So I want to talk to you about something that's very important to me. And that's how will civilization power itself for the next 100 years? So in 2100, the projected world's population is 11.2 billion. If all 11.2 billion people want to enjoy the same power usage that we do now in the United States, that's going to require burning around 0.2 yotta-joules of energy over the next 100 years. So that's a whole lot. So to put that into perspective, if we wanted to do that with oil alone, we'd have to ramp up oil production by a factor of 10 for the next 100 years. So there's no way that's going to happen. So besides being infeasible, that would contribute to catastrophic climate change. If we want to keep climate change to a level that's not ideal, but at least reasonable, say under 2 degrees of temperature increase, then only 8% of that 0.2 yotta-joules can come from fossil fuels like coal or oil. So where does the other 92% come from? So one possible source would be nuclear fusion. So fusion involves pushing together 2 smaller nuclei, and what you get out is a whole lot of energy and no greenhouse gas. So right now the sun runs on nuclear fusion, and the reaction is so energy dense that 0.2 yotta-joules would require, say, a trivial amount of deuterium found in seawater, or say just 7 months of the world's current boron production, so a very trivial amount of boron. So far it sounds like some sort of miracle fuel. Well, what's the catch? Well, the difficulty is that people have been trying this for 70 years, and so far no one has gotten out more energy than they put in. So to understand this, you have to imagine that the reaction takes place inside of a plasma. And a plasma is a 1,000,000+ degree swarm of charged particles. And these particles don't want to stay in place. The sun uses a gravitational force to keep everything in place. We can't do that, so instead we use magnets. Now, magnets, you try to squeeze it with magnets, and it can pop out the end, and you can get little turbulent ripples, and what happens is the plasma breaks up, it gets unstable, it gets cooler, and then the reaction stops. And that's what's been happening for 70 years. So this is the kind of problem that I like. It combines physics, probability, computation, mathematics, and so I was like, I want to work on this, and how can we accelerate progress? So Google is not building a fusion reactor. What we have done is we've partnered with TA Technologies, and this is the world's largest private fusion energy company. And we've been working with them since 2015. So pictured here is their 5th generation plasma generation device. And this thing is huge. It would fill up a large part of this room. And then in the center, is where the plasma is kept. So this is an elongated toroid. And the goal really is to keep this in place and prevent turbulence. And if it gets out of place, then the reaction stops. So there's magnets and neutral beams and a host of other technologies to keep it in place. Now, what's Google's job specifically? Well, our goal is to take the measurements that come from this experimental reactor, and every time the physicists do an experiment, within 5 minutes, we want to tell them the plasma density, temperature, and magnetic field on a 3-dimensional grid. So how hard is that? Well, first of all, the plasma is very, very hot. So you can't just poke it with a thermometer like a turkey. So the thermometer would melt, and you would disrupt the plasma and ruin the experiment. So what you do have are measurements along the boundary. But there's only so many measurements you can take because you can't cut that many holes in the side of this device. So let's look closely at one. Let's look at measuring of electron density, and that's done with a device known as an interferometer. An interferometer shines lasers through the plasma, and then the phase shift is proportional to the average electron density along that ray. So we have 14 lasers shining through the center of the plasma, so we know the average density along 14 lines. And from that, we want to know the density everywhere. So clearly, there's no one unique solution to this problem. And instead, we'll have a distribution over possible solutions. So we do this in a Bayesian sense. And our final output will be a probability density function for the density of the electrons given the measurements. And we can visualize that with a graph where you have the mean and some error bars. How does TensorFlow help with this? Well, so the first place is translating measurement physics into code. So let's consider the distribution for the camera measurement. So the cameras measure photons, and say we have some photons that are being emitted from the plasma. The mean number of photons reaching the camera is given by a sparse tensor, dense map mole. But we don't actually realize the mean. Instead, what we realize is a noisy mean. So there's noise due to a finite number of photons. That's Poisson noise. We also have discretization noise because we discretize space. So the TensorFlow distributions library gives you access to this normal distribution object so that this noisy flux represents a normal distribution. It has a mean. It has, you can draw samples. You can compute the PDF and so on. That's not all, though. We also have an analog to digital conversion process that we model as passing this normal distribution through a nonlinear response curve and then digitizing it to 8 bits. So at the end, this digitized charge is another distribution object that has an ability to take samples. You can compute the probability mass function because it's discrete, and so on. Now, since we want to be Bayesian, we can assemble a number of these distributions, giving us a likelihood and a prior and so on, with the goal of producing a posterior. And then we do Bayesian inference. So now to do inference, we do this in 2 different ways. The first way is variational inference, which amounts to minimizing a loss function. And by minimizing that loss function, you get an approximation of the true posterior. So this minimization is done just like any other TensorFlow minimization. For example, we use Atom Optimizer. The second way is using Hamiltonian Monte Carlo. So the TensorFlow probability library gives you access to a number of Monte Carlo samplers, and the Hamiltonian Monte Carlo is one that uses gradients in order to help you take samples faster. So notice in both cases, we're using auto-differentiation. Here, whether we're taking gradients of this loss or whether we're taking gradients to do Hamiltonian Monte Carlo sampling. OK, so popping up a level, you'll notice we're not doing deep learning. Instead, we're doing an inverse problem whereby measurements given to us from physicists are translated into a reconstruction of some physical state. So there's a few differences I want to highlight. First of all, there are no labels that are given to us. The natural label here would be a 3-dimensional image of the actual plasma. But we're the ones who are telling people what the plasma looks like, so we're the ones actually producing the labels. So given that there's no labels, you might be tempted to say, well, this is an unsupervised learning technique like word clustering. There's a key difference, though, that here there really is a right answer. There really was a plasma out there, and if that plasma doesn't fall within our error bars, we've made a mistake. And also, you'll notice that our graph here models physics rather than generic functions. So it's a bit more constrained than these deep neural networks, but that allows us to get the right answer with no labels. So at the end of the day, TensorFlow does despite it not being deep learning, TensorFlow adds value with the TensorFlow distributions and probability library. We have auto differentiation to do inference. And in order to provide answers to many measurements at once, GPUs and distributed computing is very important. So thank you very much.